Hello students, myself Dr. Mahantesh K, Associate Professor, Department of Electronics and Communication Engineering, SJB Institute of Technology, Bangalore. Welcome you all to this video lecture series on electromagnetic waves, Module 4, Class 1. In this video, we will be discussing about the magnetic forces and magnetic materials. In detail, we will be realizing the force exerted on a moving charge and the differential current elements with its force acting on the charge which is moving and force between differential current elements. In magnetic materials, we are going to study properties like magnetization and permeability. We shall try to understand how magnetic field will vary with respect to two different types of magnetic materials or mediums, and try to understand what is the magnetic field in terms of normalcy and tangential with respect to the boundary conditions, and also magnetic circuit, potential energy, and forces on magnetic materials. So we have different reference books which you can refer: Hat and Buck, Tata McGraw-Hill, Engineering Electromagnetics. Also, the local author publication from Pearson, that is Fundamentals of Electromagnetics for Engineering, for this particular module. So, magnetic forces. So, what do you mean by a force on a moving charge? So, as we have discussed in module 1 in a previous video, as per the Coulomb's law, a stationary or a moving charge Q experiences electric force Fe in electric field, which is given by F is equal to QE. Now, assume that if a charge is placed in a steady magnetic field, it experiences a force only when charge is in motion. The magnetic force Fm exerted on a charge Q moving with a velocity v in a magnetic field of flux density B is given by Fm is equal to QV cross B. So here V cross B is a cross product, sorry. By the definition, the magnitude Fm can be written as Fm is equal to QVB sine theta. The unit of force, magnetic force, is given by newtons. So here you can see the magnetic force is exerted on a charge Q moving with a velocity v. That means a charge is placed in a steady magnetic field. Only then it experiences a force only when the charge is in motion. For a positive charge, the direction of Fm is in the direction of cross product of V cross B, and it happens to be perpendicular to the plane containing V and B, according to the right hand rule as shown in the below figure. Where you can see V and B has generated an angle theta, whereas Fm is perpendicular to both the plane V cross B. It is also noted from the previous figure that the magnitude of Fm is maximum when V and B are perpendicular to B, or perpendicular to each other. That is theta equals to 90 degree. And it is 0 when V is parallel to B, that is theta equal to 0. So now if we try to realize if a charge is moving in the presence of both the electric field and magnetic fields, then the electromagnetic force acting on the charge is given by a Lorentz equation. F is equal to summation of electric force and magnetic force, which is equal to Q is common into E plus V cross B. So this equation is known as Lorentz force equation, which relates magnetic force and electric force. If m is the mass of the charged particle moving in the electric and magnetic fields, then by Newton's second law of motion, we can write F is equal to ma. That is acceleration. A is defined as rate of change of velocity with respect to time. Therefore, F equal to m dv by dt is equal to q of E plus V cross B. So, tabulating the previous conditions of forces on a charged particle, you could see state of particle. When state of particle is stationary, the electric field happens to be F is equal to QE. The force, if you're trying to move a charged particle in an electric field, it happens to be F is equal to QE, and there is no magnetic field in stationary state of particle. Therefore, the total force is equal to QE when combined with both the magnetic field and electric field. Whereas when the state of particle is moving, charge experienced the force with respect to the electric field is given by Fe is equal to QE, and also the magnetic force is experienced by the charge moving with the velocity QV cross B. Therefore, the total force exerted, combined fields E and B, is given by F is equal to Q of E plus V cross B. Just summarizing the previous equations obtained due to electric force and magnetic forces, and the Lorentz equation in the combined fields of electric and magnetic fields. So the previous explanation from this video could be in the form of a question: state and explain Lorentz force equation, or derive Lorentz force equation and mention the application of the solution. Or it can be in the form of what is electric force, what is magnetic force, explain and derive Lorentz force equation. We can try to differentiate electric and magnetic force as follows. The electric force is always in the direction of electric field, whereas the magnetic force is always perpendicular to the magnetic field. This is one important difference between electric force is always in the direction of electric field, magnetic force is always perpendicular. How perpendicular the magnetic force is with respect to the magnetic field. The electric force acts only on a stationary or a moving charge, whereas the magnetic force acts on both only when the charge is in motion. The electric force displaces a point charge at the cost of energy, whereas no work is done by the magnetic force. When a point charge is displaced, that is, the kinetic energy of the charge remains unchanged. So now let us try to understand force on a differential current element. A very important derivation from the exam point of view. So what do you mean by force on a differential current element? Remember from our previous video, we tried to extract the magnetic field equation from the differential current element carrying conductor of I of length dl. So here the current density J can be expressed in terms of velocity and the volume charge density as J is equal to rho V into V. Therefore, the differential charge is equal to rho V into differential velocity. The force on a differential current element IDL of a conductor carrying current due to the magnetic field of magnetic flux density B can be given as equation 1 and equation 2 as given below. Now the differential force exerted on differential amount of charge moving in a steady magnetic field is given by dF is equal to dQ V cross B based on a previous magnetic force equation. Substituting equation 2 in equation 3, we obtain dF is equal to rho v dv v cross b. But rho v into v is equal to j. Therefore, dF is equal to j dv cross b. So if you carefully observe this equation, j dv is in terms of current density over the volume, which can be equated with respect to the current density of surface, that is surface current density into ds, which is equal to IDL, which in terms of the line current or the line current density. Then the differential force exerted on rho s is given by dF is equal to k ds cross b. Similarly, differential force exerted on differential current element is given by dF is equal to IDL cross b. So integrating equation 4 over the volume, I can obtain F is equal to line integral of IDL cross b. For a straight conductor in a uniform magnetic field, the above equation can be simplified as F is equal to IL cross B. Hence, the magnitude of force on a current element is given by F is equal to BL I sin theta, where theta is the angle between the direction of current and the direction of magnetic flux density. Thank you for watching this video. In the next video, we shall discuss more upon differential current elements and the differential forces exerted due to differential current elements.